Now that we finished the total derivatives and total partial derivatives, we are ready to deal with implicit functions here. But before we go to implicit function theorem, maybe we should answer a simple question. What is an implicit function? Okay, let's start with what is explicit function. Explicit function is a case that we are used to. So y is defined, for example, y is defined as a function of some variable x. Knowing the value of x, we can directly calculate y. Give an example. Let's just say that y equals 3x to the power of 4. Right? Knowing the value of x, we can easily calculate the value of y. However, we could write the same thing differently. Look, let's just say that we're going to use capital letter F to define a function of two variables, y and x. How does this function could look? For example, y minus f of x, or simply put, y minus 3x to the power of, okay, equals to 0. Okay, let's start like this. Look, what have I done here? Not much. Look, what I did is that I took this function and rewritten it in a different way. Look, if y equals f of x, then of course y minus f of x must be equal to 0. Right? But look, in this case, we are not seeing y as a function of other variables on the other hand side of the equation. So, going back to our example, we could rewrite this in a following way. Now look, this equation over here is very specific. Why? Because look, equation f y x, and this is very important. It may, so it only might imply function y equals f of x. So look, if we have equation in this form, we might say that in a very specific circumstance, this equation may imply this function. And in this case, we call this an implicit function. Okay, so what does it mean? Look, basically, we might have an equation where we have all the variables and it's equal to 0. This is actually quite easy to get it to this form. We simply put everything from the equation to the left-hand side, so we are left with 0. As it turns out, this very simple result has a tremendous economic and mathematical, but then economic implication. What are those implications? Look, let's start by asking a very important question. And this question goes like this. When equation in the form when equation in the form y x1 x2 until xm equal to 0 equals to 0 defines implicit function y equals f of x1, x2 until xm. Around some specific point in the domain. Okay, so what do we have over here? When equation in the form, look, we've got it here, equation in the form, when here we have some one variable that later on we call endogenous, and a number of n different exogenous variables. In this form, define a function where y can be expressed as a function of all these exogenous variables around some specific point. Right? So we are given this equation and we are trying to find out when this equation actually implies this one. Well, it turns out that the answer to this question is implicit function theorem. Of course, you don't need to know it by heart. This theorem is long and boring. However, we need to just understand what it means so we are able to actually use it. Okay, so let's go step by step by what is in the theorem. Okay, so given function, the function in the form f as a function of y, x1, x2 until xm equals to 0. Yeah, given. If, and here we have two conditions. First, the function f has continuous partial derivatives fy, f1, f2 until fm, where of course subscript here simply tells us with respect to which variable we differentiate this equation, right? So fy is just derivative of function f with respect to variable y, and f3 would be partial derivative of function f with respect to variable x3. And look, in all the cases where we will be actually dealing with, we will assume that those partial derivatives are continuous. So this is not the key to us. However, there is a second condition. At a point y0, x10, x20, xm0, satisfying this equation, derivative of f of y must be non-zero. So it's different than 0. This is the main condition. This is the condition we will have to check before we can use the theorem. And look what is happening then. There exists an n-dimensional neighborhood of point x10, x20, xm0 that we will call n, in which y is implicitly defined function of variables x1, x2, x3, xm. So we've got that implicit function. So basically, what we learned, so given an equation in this form, as long as this condition is fulfilled, around some specific point in the neighborhood, we can say that this implicit function is defined. Now, look, this implicit function satisfies x1, 0, x2, 0, xm, 0. So it is an identity right at this point at which we evaluate. Look, for us, it usually is going to be equilibrium. So we are evaluating this at equilibrium, and we're trying to see what happens if we are moving to the next equilibrium, right? Comparative static derivatives, as usual. Right? And it also satisfies the equation that we had at the very beginning for every n tuple. So, a set of coordinates in M space in the neighborhood of n, thereby giving our function the status of identity. Identity means that this and this are exactly the same in that neighborhood n. And now look, moreover, the implicit function is continuous, assuming those conditions are fulfilled, and it has continuous partial derivatives. So look, we are going to use this function, and we're going to try to use this function in order to calculate those derivatives. But those derivatives are derivatives of this function. So our f1 from here is partial derivative of y with respect to x1. Okay, so now that we know when this implicit function is defined, we can start thinking about calculating derivatives of implicit function. Okay, so let's move to that. Okay, so again, we are starting with function that we are given. So f, y, x1, x2, xm equals to 0. Now look, I can very easily calculate total differential of this expression. Well, this will be partial derivative of f with respect to y dy plus partial derivative of f with respect to x1 times dx1 plus partial derivative of f with respect to x2 dx2 plus partial derivative of n with respect to f. We go on like this, and so partial derivative of f with respect to xm times dxm, and it all equals to 0. Now look, again, just as before, because we would have to write too much, let's simplify. So let's denote this derivative as fy. Now we've got dy plus f1 dx1 plus f2 dx2 plus, and go on like this until fm dx, and it all equals to 0. Okay, so it wasn't that bad. We easily calculated total differential of this function. But this is not all. Look. What I can do over here, give me a second. Yeah, and now look, we said, let's assume that the conditions of the theorem are fulfilled, right? Which means that basically fy is different than 0, right? Now, we know that this function implies this function. Now we can calculate, now what we can do is to calculate differential So we've got dy equals to f1 dx1. And of course, f1 is equal to partial derivative of y with respect to x1. And generally, fi is partial derivative of y with respect to xi with I equal to 1, 2, until f. Right? And plus f2 dx2 plus until fm dxm. Okay, now let's notice a very simple thing. Look, dy, then we've got over here is over here. So look what I can do right now. I can simply take this expression and substitute it in the equation we've got above. And what are we going to get out of it? We're getting that fy times f1 dx1 plus, okay, this is all I'm going to write from this moment on, plus fm dxm plus f1 dx1 plus f2 dx2 plus fm dxm. And now notice one thing. Look, each expression in the parentheses has there is one expression in the parentheses with dx1, and there is one expression with dx1 outside. There would be one expression over here, f2 dx2, right? So we will have dx2 over here, dx2 over here, and then we will have dx3, dx4, dx5 until dxn and dxn. If this is the case, why not just reorganize it in such a way that all the expressions with dx1 are together, dx2 are together, dx3 and until dxn are together. So, look, we need to combine this and this. So we will have fy, f1 d plus f1 times dx1, right? Those are expressions associated with dx1. Then we will have the second one, fy times f2 plus f2 whole thing times dx2, right? Now we've got all the expressions with dx2. And we would go on like this until we would arrive at the last expression. Everything checks out. Oh, sorry, I forgot 0 over here, but I hope this is all pretty obvious. And now, finally, we've got fm plus, fy, fm plus fm times dxm equals to 0, which solves our problem with the last expression. Okay, now that we've arrived here, the question is, when this is an identity, which what I mean is that when left-hand side of this equation is equal to the right-hand side of this equation. Well, this happens if and only if all those expressions are equal to 0. Okay, so if if this is the case, what we must have, look, when we calculate derivatives, right, we're assuming that those are different than 0. So if those are different than 0, then this must be equal to 0, this must be equal to 0, and this must be equal to 0. So things in parentheses must be equal to 0, right? So we must have a case where Fy times F1, Fi, right? 1, 2, 3 until n plus Fi equals to 0. For I equal 1, 2 until n. For all. Now, if I'm gonna take this expression that you see over here, and I'm gonna work with it, but not much, turns out that we're gonna get something that is called implicit function rule. And this is the rule that allows us to calculate derivatives of the implicit function. How do we go about it? Look, we start from this. And remember, what we are interested in are derivatives of implicit function. So y is a function of x1, x2 until xn, right? So we want to know what is f1, f2 until fn. We can easily calculate it out of this. So we get that fi equals to negative fi, and fi is equal to negative fi over fy, and I hope you can see that, of course, fy must be different than 0, and of course this is for I equal to 1, 2 until m. And this formula that you see over here is the implicit function rule that actually allows us to obtain some incredibly specific, in a sense, detailed results in cases when we know very little about the functional form of different economic equations. Okay, but before we go to economic examples, let's just do a couple of very trivial mathematical examples. Because I know that this might sound strange and complicated, however, using it, very simple. Okay, so let's start with the first example. Let's just say that our function f yx is equal to y minus 3x to the power 4 equals to 0. Right. Look, we know this. This is very easy, right? Out of this, we can easily get that y is negative 3x to the power of 4, right? And dy dx is simply equal to 12x to the power of 3, right? Nothing complicated. However, we can also find this using implicit function. Because look, we are looking for derivative dy dx. So, first thing I need to do in this case is to apply the formula, right? I start with minus, and first I differentiate this function with respect to x. So I'm getting that this is negative 12x to the power of 3. Then I divide this by derivative of the big F with respect to y, which is 12x to the power of 3. You clearly see that the rule works. Of course, remember that this case is trivial. In this case, we actually don't need to use the rule. However, what if we want to know, if we want to know what is derivative dy dx if f, y, x, w is equal to y to the power of 3 x squared plus w to the power of 3 plus y x w minus 3 equals to 0. Now, doesn't matter how smart you are, solving this equation not gonna be that easy, right? But this is why we have this rule. We don't need to solve this equation to obtain this derivative, right? If I want to know, actually this one is partial derivative. I'm really sorry because we have two variables. Look, we want to know derivatives of this function, right? Actually, let's just calculate one. dy dx. Okay. Again, we need to just use the formula. So we start with the minus. And what do we do at the top? First, we differentiate this equation with respect to x, right? The one we had at the bottom. So, if I differentiate this with respect to x, I'm getting that this is 2 y to the power of 3 x plus 0 plus y w. And that's it. Right? Now, the second thing I need to do is to, over here, differentiate this equation with respect to y. So I'm getting that this is 3y squared x squared plus x w. And this is our result, which will of course hold as long as 3y squared x squared plus x w is different than 0. Okay, so this is all we need to know about the implicit function rule. Now what we're gonna do are the applications of these rules, first to the market model and then to national income model. Okay, thank you for your attention and see you in the next video.